Hello students, hope you are all safe and sound at home. In the last class we have discussed the function and the domain range of a function and also how to represent a function symbolically. And also we have studied what are the different types of real value functions which we have studied in last week. Now let us just recall the definition of function once again and then we will move on to the next concept, that is types of functions. And please pay attention because the types of functions are very important, and if you don't understand the concept in the beginning, then it will be very difficult to solve the problems. So now let us recall what is a function. So already we have studied function is nothing but a special type of a relation. It is a relation only, but it has a particular condition. Or in other words, you may say it satisfies a particular or a rule. And what is the condition? Here, if you represent a function f from x to y, already we know x represents the domain and y represents the codomain. Now, every element in x should be related to one and only one element in codomain y. That means here actually there are two conditions. First condition, every element in x, that is domain, should be related to some element in y. And the other thing, each element must be related to only one element. So we can't leave any element in the domain x. But the codomain and range need not be equal always. Range is nothing but the set of all images. Codomain and range need not be equal, but the first set x should be the domain implies every element in domain x must have an image. Now, let us consider the different types of functions. Types of functions. Already we have studied constant function, identity function, polynomial, rational, modulus, greatest integer, signum function and all these things. But now we are going to study few more different types. That means depending on the mapping of the given function, we are defining these types. Now, before starting with the definition directly, let us consider an example. Using the example, we will understand what is the meaning of this function and afterwards we will get the definition. Now, we are considering that function f of x is equal to 2x. So, what we do, we consider the set A or set x and y as the domain and codomain. So let us draw the arrow diagram only. This is our set x. This is our set y. Set x contains the elements 1, 2, 3, 4. For set y, elements are 1, 2, 3, 4, 5, 6, 7, 8. So now we are defining a function from x to y, that is f of x is equal to 2x. So x is nothing but the element of set x and 2x, this is nothing but y only, which belongs to set y. So 1, x value is 1. So f of 1 I have to consider. So f of 1 is nothing but 2 into 1. So 1 is related to 2 here. Understood? Then when I take x is equal to 2, f of 2 means 2 into 2. So 2 is related to 4. F of 3, similarly the next one is 3 to 6. When I take x is equal to 4, f of x is 2 into 4, that is 8. So now, clearly from the diagram, we can understand the elements in the domain x is related to a unique element. They are not related to the same element, they are having the different elements. Similarly, if I continue the elements here, to write the elements in x and y, I may take the next element as y, and here also I have to take x is equal to y means y is equal to here, it should be 10 should be included. So this type of function is called 1-1 function. So here the name 1-1 indicates one element in the domain has exactly or it has one image. But be careful, if you take any element in the domain x here, the images should not be same. The images must be different. Or in other words, different elements have different that is the meaning of one-one function. So let us write down the definition of one-one function and afterward we will move on to the next one. So one-one function, or it is also called injective. One-one function or injective. In examination they may use the term one-one or injective, but don't get confused, both are one and the same. So let us write down the definition, take down the notes now only. A function f from x to y is called one-one function if every element in domain has one and only one image in codomain. Every element in domain, here domain is nothing but x, so here we may also write every element in domain x has one and only one image in codomain 1. This is the definition. That is nothing but for all x not equal to y, f of x not equal to f of y, where x and y belongs to domain of the function. X and y are domain of the elements of domain, and f of x not equal to f of y if you are taking different elements in the domain. But when we are solving the problems in the coming classes, we are not using the same definition. That means we are using the contrapositive of the definition. Already in first year mathematical reasoning you have studied what is contrapositive. If we are having a condition, if then it is P implies Q, then the contrapositivity is negation Q implies negation P. And when we consider the truth value, both represents, or in other words, we may say both the conditions are equivalent. That means they will give the same meaning. So here also we will be proving the problems, or we will be solving the problems using the contrapositive. In other words, we may write, in other words, f of x equal to f of y implies x is equal to y for all x and y in the domain x. Remember, we are using the condition f of x equal to f of y implies x equal to y for every element in the domain. But the meaning of one-one function is different elements have different image. If the images are same, then the elements are also same. Otherwise, the function is not called one. So remember, one-one means different elements, different image. Now, let us consider the next one, that is many-one function. Many-one function is the name itself says many elements have one image. To make it more clear, we can take the example of the function f of x is equal to x square. So let us take the elements -1, -2, 1, 2 in our domain x, and in y we are having 0, 1, 2, 3, 4, 5. F of x is equal to x square. -1 the square is nothing but 1. -2 the square is 4. 1 square is again 1. 2 square is also 4. Here, no doubt it is a function because every element in domain has an image. But what happens when we look at the images? in what way the elements are related to the elements in codomain. The elements -1 and 1, both the elements are having the same image. Similarly, -2 and 2, they are having the same image. That means the condition for 1 function doesn't hold, or different elements have same image. Therefore, this function is called many-one function. As the name itself describes the function here, many elements have one image. That's why it is called many-one function. So let us write down the definition. A function f from x to y is called many-one function if two or more than two elements in domain have the same image in codomain. Two or more than two. It is also possible. More than two elements have same image in codomain. That is, x not equal to y, but f of x is equal to f of y for x comma y belonging to the domain x. X and y both are different, but their images, that is f of x and f of y, are equal. This type of function is called many-one function. So make sure you know the difference between the one-one and many-one function. One-one means different elements, different image. Both are different. But when you consider many-one, many elements, same image. Now the next one is onto function. Onto or surjective. Now, if you are having a set S and a set Y, and from X to Y we are defining a function. The elements in X are 1, 2, 3, 4. Elements in Y are A, B, C. Let us see. And the element 1 is related to A, 2 and 3 are related to B, and 4 is related to C. Now here, look at the function. No doubt it is a function, but different elements are having the same image. No doubt it is not one, but when we are discussing the condition for onto, what is the condition here? Every element in the codomain, be careful, not the domain. Every element in the codomain is image of some elements in domain. So here A is image of 1, B is image of 2 as well as 3, C is image of 4. No doubt different elements are related or they are having the same image, but every element in codomain is an image of some element in domain. This type of function is called onto function. Either this is the definition, or we may also say the codomain is equal to range of the function. In that case also the given function is on. Let us write down the definition. A function f from x to y is called onto function if every element of y, here y is codomain of the function, every element of y is an image of some element in domain x. Every element in y is an image of some element in x. That is, for all y in set Y, there exists, you know the representation, you know the symbol, there exists X in the domain X such that f of X is equal to Y. This is the definition of onto function. Or in other words, we may also say a function is said to be onto if range of the function is equal to its codomain. A function is said to be onto if its range is equal to codomain of the function. And when we can use this definition? For all the problems we can't use the definition range equal to codomain or not. But if the problems are safe but are already there is some real valued function which have studied in previous year, then easily we can find the range and then we can compare whether the range is equal to codomain of the function. But when we are dealing with a few other problems, we'll have to use the definition, that is, for all y in codomain y, there exists an element x in domain such that f of x equal to y. Now, let us consider the next one, that is bijective function. Here, bijective function is nothing but a function which is both 1, 1 and onto. Or in other words, a function which is both injective and surjective is called bijective function. So remember, the given function f is 1, 1 but not onto. Or the function f is not 1, 1 but onto. In that case, the function will not be bijective. For a function to be a bijective function, the condition is it should be both 1, 1 and onto. A function f is said to be bijective if it is both 1, 1 and onto. If it is both 1, 1 and onto, then the given function is bijective function. So already we have studied what is 1, 1. 1, 1 means different elements, different images. Many 1, different elements, same images. And onto means codomain and range both are same. Or in other words, we may say every element in codomain must have a pre-image in the domain. So now let us consider a few examples where we will be discussing whether the given function is 1, 1 and onto. Now let us consider a few examples where we have to study or where we have to check whether the given functions are 1, 1 and onto. Now the first question is, show that the function f from r star to r star defined by f of x is equal to 1 by x is 1, 1 and onto. Already it is given, we need to prove the function is 1, 1 and onto, where r star is a set of all non-zero real numbers. That means the number 0 is not included in the domain as well as the codomain. And also we have to check it further. Is this true? If domain r star is replaced by n being set of natural numbers, with the codomain being same as r star. That is nothing but first, after proving the function f of x equal to 1 by x is 1 and onto, we need to replace the domain r star by n. So that will be a function from set of naturals to set of non-zero real numbers. So let us first prove the function is 1, 1 and onto. After that we will come to this second condition. So f of x is equal to 1 by x and x belongs to r star. R star means set of non-zero real numbers implies x not equal to 0. So 1 by x is a real number. Only when x value is 0, the function cannot be defined. But that value is not included in the domain as well as the codomain. Now first we need to check whether the function is 1, 1 or not. So what we do? Using the definition, already we have studied different elements, different images, but when we try to solve the problems, we are using the contrapositive. That is, if the images are same, then we have to prove the elements are also same. So let us consider x comma y belongs to the domain R star such that f of x is equal to f of y. F of x is 1 by x. So here I write 1 by x, but what is f of y? Replace x by y. So that implies 1 by x is equal to 1 by y. But when we cross multiply or when we simplify that further, this is nothing but x is equal to y. We are considering f of x is equal to f of y and we are getting x equal to y. Therefore, f is 1. Now, in order to prove the function is onto, here we can't find the range directly. So we can't use the definition range equal to codomain. So we are using the first definition. That is, for every element in codomain, there exists an element x in domain. We have to write. So what we do? We will consider that y belongs to codomain R star such that f of x is equal to y. That is, y is equal to 1 by x. F of x is nothing but the definition is 1 by x. So y is equal to 1 by x. But that implies x is equal to 1 by y. The value of x is 1 by y and here y is not equal to 0 because y belongs to R star, the set of non-zero real numbers. Now, we will consider the function f of x. Now, in place of this x, we will substitute the value of x which we got using the definition of the function. So, x is 1 by y, but f of x is 1 by x only. Now, in place of x, we will substitute the value 1 by y. This is equal to 1 divided by 1 by y. Taking the reciprocal, this y goes to the numerator, that is equal to 1. So, for the value x is equal to 1 by y, we are getting f of x is equal to 1. Therefore, f is on. This is how we will have to prove whether the function, we will have to check whether the given function is onto or not. Already we have proved the function f given by f of x is equal to 1 by x is 1 and on. Now the next condition we have to check is this true if domain R star is replaced by n? So let us consider, let g, we are considering this new function as g. G be a function from n to R star defined by g of x is equal to 1 x. So we are considering this new function as g and g of x is equal to 1 by x. So in order to check whether the function is 1 or not, so what we do? Let x and y belongs to the domain of the function here is set of naturals. X and y belongs to n such that g of x is equal to g of y. That implies 1 by x is equal to 1 by y, or you may write x is equal to y. Therefore, the function g is 1. But when we consider the condition on 2, here look at the domain and codomain. Domain is set of natural numbers and codomain is set of all non-zero real numbers. So now what we have to do is, if you want to prove the function is onto, then for every element in this R star, there must be an element or pre-image in n. But when we consider the number, let us say Let 1.5 belongs to R star. But for this number 1.5, whether we have pre-image in the domain N or not, we have to check. If we are getting a pre-image, then we can easily conclude. But for every number, there should be a pre-image. So we are taking one particular example here. So let 1.5 belongs to R star, but there is no X in the domain N for which X is equal to 1 divided by 1.5, because 1 by 1.5 doesn't belong to the set of naturals. Therefore, G is not onto. When we replace the domain by set of natural numbers, the function, no doubt it is 1, but it is not onto function. Now in this question, we need to check the injectivity and surjectivity of the following function. Injective means 1, surjective means onto. So for these three functions, we have to check whether the function f is 1, and onto. The first question is a function f from n to n. A function defines the set of naturals given by f of x is equal to x square. Whether it is 1, and onto. How to prove that? So we will consider the condition for 1. So what we do? We will take any two elements, any two arbitrary elements from the domain. So let x bar belongs to the set of natural numbers such that f of x is equal to f of y. That implies x square is equal to y square. Or you may write x square minus y square is equal to 0. Directly also we can take the square root and we can do x is equal to 1. But if you have it, how it comes? We can also write this like x square minus y square equal to 0. So what it implies? Already we know x square minus y square is x minus y into x plus y equal to 0. Since x and y both are natural numbers, x plus y cannot be 0, isn't it? Because we don't have any such natural numbers where the sum of two natural numbers is 0. So this implies x minus y equal to 0 because x plus y not equal to 0 as x and y are natural. So we are left with only one condition, that is x minus y equal to 0 implies x is equal to y. So the function is 1 implies f is 1. But when we consider onto condition, so what happens? F of x is x square. But already we have studied the square of a real number or square of any natural number. Any number you may take, real number, integer, or even only the natural number. In that case, what happens? Its image is always non-negative number. And here, x square, f of x is equal to x square, and the function is defined in set of natural numbers. So clearly we can say the function, its range is set of positive numbers. Set of positive numbers. And here clearly the range includes the values 1, 4, 9, 16, 25 and so on. That means the codomain is n natural numbers. Codomain and the range both are not equal. So without even proving using the definition directly also we can conclude here, since the range is not equal to codomain, the function is not onto. Here for onto condition, we may write here range is equal to 1, 4, 9, 16 and so on, which is not equal to n. That is nothing but codomain. Therefore, f is not on. The given function is 1, 1, but it is not on. Moving on to this second example, f from set of integers to integers z to z given by f of x is x square. Same definition, but the domain and codomain are different. Now, here there is no need to consider any two elements in domain and to check whether the images are same or different. Because in the previous example, we are taking an arbitrary element x and y and then we are proving. But here, directly we can say clearly minus 1 the square is equal to 1 and 1 square is equal to 1. Implies here, look at the image, both are equal to 1, but minus 1 is not equal to 1. Elements are different, but the images are same. That is minus 1 and 1. Or in other words, we also write f of minus 1 is equal to f of 1, but 1 is not equal to minus 1. Therefore, f is not 1. If we consider the next condition, that is onto or not, again, since the function is defined in set of integers as f of x is equal to x square, the set of, here be careful, the set of the images is nothing but the set of all non-negative integers. Set of all non-negative integers. Or in other words, you may say the numbers, integers minus 1, minus 2, minus 3 and so on. They are not at all included. And also few more elements, that is for example 3, 5, 7, 6, all these are not image of any element in Z. So directly we can write without any verification or without any proof, that is also range not equal to codomain. Therefore, f is not onto. Now, same as the previous example, but the function is defined from set of real numbers to real numbers as f of x is equal to x square. Again, here also the function is not 1 because when we consider the function f of x is equal to x square, different elements are having same image. That is f of minus 2 we may take, which is equal to 4, because in other words also we may write there is nothing but minus 2 the square, which is equal to 4, and f of 2 is equal to 4 also, but 2 not equal to minus 2. Therefore, f is not 1. And when you consider the range, you may say, or when you consider the codomain, or in other words, every element in codomain is not an image. If you take the negative number, they are not at all image of any element in the domain R. Because when we consider x square, the image, or you may say the values, are always non-negative. Since the range is set of all non-negative real numbers, the function f is not onto. So the function defined in set of natural numbers is 1, 1, but not onto. In set of integers, it is not 1, 1, not onto, neither 1, 1 nor onto, we may say. And in set of real numbers also, the function f of x is equal to x square is neither 1, 1, not onto. So in any of these cases, the given function is not bijective. Now, look at these two questions. A function f from n to n given by f of x is equal to x cube, and the next one is f from z to z given by f of x is equal to x cube. Even though the definition is same, its domain and codomain are different. And this question also, here also you have to check the injectivity and subjectivity. And these two questions are your assignment problems. Remember, watch the previous examples and also solve these two examples. Because in examination, sometimes they will ask these type of questions for 2 marks. You have to check the injectivity as well as the subjectivity. Now, the next question here, look at the question carefully. Prove that the greatest integer function f from r to r given by f of x is equal to box x, that is nothing but the representation of greatest integer function, is neither 1 1 nor onto. Neither 1 1 nor onto, where box x is the greatest integer less than or equal to x. Already we have discussed what is greatest integer function and how to find the greatest integer of the given real number. Now we have to prove the function is neither 1 1 nor onto. So remember, already we have discussed in relations also. If you are proving it is 1 1, then you have to prove it in general. Then you can't take any particular example. If you are proving it is not 1 1 and onto, not onto, then if you give an example, that is sufficient. One particular example is sufficient to prove the function is neither 1 1 nor onto. So let us write down the definition of the function. Given that f of x is equal to greatest integer of x. Clearly, the greatest integer of 1.5, what is it? The integer plus proper fraction. So 1 plus 0.5 we will be writing, and the integer is nothing but 1. And the greatest integer of 1.9, if you consider, this is also equal to 1. That is, f of 1.5 is equal to f of 1.9. Both are equal to 1, but 1.5 is not equal to 1.9. So now we conclude the function is not 1 1 because different elements are having the same image. Therefore, f is not 1 1. And when we are considering the onto condition, onto means the codomain is equal to range. But when we are discussing the greatest integer function, already we know the domain is set of real numbers, but the range is set of all integers. Even if you are taking the positive real numbers or negative numbers or 0, the image of each and every real number is nothing but an integer. So let us directly write it also. Since the range of greatest integer function is set of integers, codomain is not equal to range. Codomain is nothing but set of reals, that is r not equal to z. Hence, f is not onto. I hope you understood this problem. Remember, if you are considering such example, that means if you are proving the function is not 1 1 or not onto, in that case, just give an example. That is enough to conclude. The next question is, show that the modulus function f from r to r given by f of x is equal to mod x is neither 1 1 nor onto. As we have discussed in the previous example, here also if you give an example or if you give a particular result, then also it is sufficient. So how to prove the function is not 1 1? Not 1 1 means different elements, they have same image. So let us consider 1 1 condition. F of x is equal to mod x. But already we know what is the definition. No doubt the domain is set of real numbers, but depending on the value of x, the definition varies. If x is less than 0, mod x is minus x. If x is greater than or equal to 0, mod x is equal to x. Remember, when you are solving these type of problems, if the definition is not clearly given in the question, then you have to write down the definition first of all, and then you have to continue the solution. So f of x is mod x, that is minus x. If x is negative, it is plus x. If x is non-negative, don't say positive because 0 is also included and 0 is neither positive nor negative. Now, consider modulus of minus 5. Mod of minus 5, according to the definition, minus 5 is negative. So we are using the first definition. Minus of minus 5. Minus of minus becomes plus 5. And mod of 5 is equal to 5 also. The image is same, but the elements 5 and minus 1 are different. But 5 not equal to minus 5. Therefore, f is not 1, 1. It is very easy to prove these type of questions. Only have to provide an example, that is sufficient. Now for onto condition. How to prove whether the given, how to check whether the given function is 1, 2 or not. Here clearly it is given. We have to prove the function is not on. How can we prove that? Just recall the range of modulus function. The range of modulus function is set of all non-negative real numbers. Therefore, what happens here? Codomini set of pairs, but the range is non-negative real numbers. Clearly, both are not equal. Therefore, f is not on 2. If you want, you can write down the reason. Are not equal to, or in words also you may mention. Are not equal to closed interval 0 to infinity. This is your codomain and this is your range here. Codomain and range both are not equal and hence the function is not on. I hope you understood the concept of 1, 1 function, onto function and many 1 function. Remember, if the given function is both 1, 1 and onto, then only it is called bijective. If any one of them is not true, that means if the given function is not 1, 1 or it is either not 1, 1 or it is not onto, in that case also the function is not bijective. After watching the video, write your name and section in the comment box and also remember to write down the notes in your notebook. And we will continue with the few more problems in the next class. Thank you.